Okay, let's talk a little bit about radiation types. And some inspiration for this presentation came from Jonathan Letham's Fortress of Solitude. In the Origin comics, you learned how superheroes started, the answer generally being radiation. So our objectives for today is we're going to define radiation and give examples of the different types, right, and sources. Let's describe the sources of radiation, right? So we'll differentiate between types and sources. We'll explain equivalent dose and effective dose as well as how to calculate those things. And we'll discuss the significance of the sievert as a unit of measure. For the most part, I'm going to lean towards sievert when it comes to things like effective dose. And then we'll organize roles of personnel for handling various radioactive sources. Okay? So, now I know that we just kind of blew through a lot of information last week, and I've said that once already, but this week we're going to kind of unpack some of this stuff and make sure that it's distilling and that it's making sense in our heads. So the very first thing that we'll do is just define what radiobiology is, and this comes from Washington Lever, page 59. Radiobiology is the study of the sequence of events following the absorption of energy from ionizing radiation, the efforts of the organism to compensate, and the damage to the organism that may be produced. So what is radiation? Radiation is an energy that has the ability to do work, right? And radiation relates to energy in that radiation refers to kinetic energy that passes from one location to another and can have many manifestations. So this means there's a bunch of different types of radiation that exist. To that point, there's also ionizing and non-ionizing radiation, right? So it's good for us to differentiate between a radiation that might be ionizing versus one that's non-ionizing, because the non-ionizing stuff, while it could potentially cause some damage, it's not going to cause ionization processes, right? So the electromagnetic spectrum can be divided into largely two different parts, which is the ionizing radiation. So this is anything higher than 10 electron volts, so that's ultraviolet and higher. High energy ultraviolet and higher is going to be ionizing radiation. Anything below ultraviolet is not going to be ionizing. So examples of that are the lower energy ultraviolet radiation, visible light, infrared rays, microwaves, and radio waves. So a microwave is not going to ionize you, right? But you still shouldn't stick your head in it because what? What is it going to do to your atoms? Yeah, it's going to heat them up. So it has a different form of excitation that's going to occur, and it's going to be manifested in the form of heat.
What page did you do this on?
This information is in our textbook beginning at chapter 2. The Washington Lever is the radiation therapy textbook. So I pulled that example from the Washington Lever. But if you look on page 16 in our textbook, yeah, that's the Washington Lever book. Yeah, that's a different text. You could also find an example of that in Bouchon. It's like chapter 32 or 33 in Bouchon. So let's talk about what ionizing radiation is real quick. It's anything that can convert atoms into ions, right? So it can ionize material. And we use it for creating images, like in terms of our context here. We're going to be using different forms of ionizing radiation to create images. And yet it has the undesirable effect of causing some biological damage. Here is an example of that ionization process where an electromagnetic wave is influencing this atom and it has knocked an electron free. And so now we have an ion pair, an electron which is negatively charged, and an atom which has now got a positive charge of 1 because it lost 1 electron. So some sources that are listed in our book, Table 2.3, Table 2.4, and Figure 2.2 in the textbook look at these different sources, and it's important to make sure that when we're talking about sources, we're using this word appropriately. When I use source, I'm talking about whether it's artificial or a natural radiation. Like, where did they get the stuff from? Was it produced from my X-ray tube, or was it dug up out of the earth, right? Is it radon that trickled up into my basement, right? And interestingly enough, among those naturally occurring radiation sources, there's actually stuff inside of your body right now that's ionizing the tissues of your body. If you ate a banana this morning like I did, you are being irradiated by the K40 that was in the banana that you ate, right? If you were down in the basement last night working, trying to kill the cockroaches like I was because I live in Midtown, then it's possible that you were exposed to some radon gas, and now that radon gas is going through a decay process inside of your body. But every single one of us is emitting radiation that's affecting ourselves right now. That's what we're going to call internal radiation, and that is a form of natural radiation. Versus types, right? Types of radiation is going to be electromagnetic versus particulate. And I made a separate slide for this because I was like already an X-ray tech before I finally understood that there was a difference between particulate radiation and electromagnetic spectrum type stuff. This is particularly important when we're talking about radiation therapy applications because they will use, for example, an electron beam, which is a particulate radiation form to treat superficial cancers, right? To treat superficially, they're going to actually use a particle to treat it. Versus when they're treating something deeper, they will use electromagnetic radiation and a Bragg peak to get to that deeper structure. There's some types of electromagnetic radiation. These are things like radio waves, microwaves, infrared, visible light, which we mentioned earlier. And then one example of something that's not electromagnetic radiation, interestingly enough, is ultrasound. Ultrasound is not electromagnetic radiation. It is a mechanical vibration. The machine is actually producing a mechanical vibration that's producing sound waves. So here is that electromagnetic spectrum that we should be pretty familiar with by now. And we know from the spectrum that there's an inverse relationship between wavelength and frequency, right? All of this stuff, for our purposes in this class, all of this stuff is traveling at the same speed. So speed for us is going to be a constant. What is that constant? Good, speed of light. So if we know that constant, we can calculate for example, frequency if we have wavelength, or wavelength if we have frequency. We just plug that constant in and then divide or multiply or whatever. But it is important that they are inversely related. And one of the examples that I use sometimes with like a freshman class is if I had a power cord and I was going up and down with the power cord, right? So it has a nice long wavelength. It doesn't have very much energy, right? But if I start going like this with it, so it has a really short wavelength, it has quite a bit of energy, right? So they're not traveling any faster though. It's not as though they're going faster. They're literally just vibrating more as they travel. So these electromagnetic waves are characterized by their frequency and wavelength, and they have a dual nature. Sometimes they're referred to as, a wave-beam duality or wave-particle duality theory. And that means that it can travel through space in the form of energy, but they can interact with matter like it's also a particle of matter. So it kind of has the best of both worlds. It can travel like a wave, but it can interact with matter as though it were matter. And there's a table in our book that kind of deals with these different kinds of frequency on page 17. In terms of these basic units, we have this activity, which we talked about earlier, is the amount of disintegrations per second in a radioactive source versus exposure in air. So when we're talking about the electromagnetic spectrum, we're only talking about the potential to expose things. It does not have some decay constant or something like that, right? It just travels, and in fact, unless it interacts with something, it's not going to lose any energy. It's just going to keep on going. As far as we know, it just keeps on going. And what we've said is that these ionizing radiations have the ability to do some kind of work inside of the tissues of our body. Now, one of the interesting things about this, right, is the average cell, right? The average cell on a year will repair over 400 DNA breaks, double-strand breaks. So these can be caused by chemicals, they can be caused by radiation, they could be caused really just by mechanical vibrations, right? So the body has, each cell, if you can imagine how many billions of cells are in your body, 400 times each one of those cells is going to have to repair some kind of DNA break every year. So I want to stress that even though radiation causes these interruptions of the DNA, our body has a natural response to it. Our body is able to repair that. Cancer, on the other hand, doesn't, right? And this simple principle is why we use radiation to treat cancer. It lacks the ability to repair itself, whereas DNA can. Our cells can. So in terms of part 2 for thinking about radiation, the amount of energy transferred by these electrons, transferred to the electrons by ionizing radiation is the basis for what we call radiation dose. So we have these things traveling through the air, causing an exposure in the air, and then it strikes an atom or a molecule in my body and ionizes that, forms an ion pair. And now whatever it does, whatever ramifications of that ionization event is what we're going to refer to when we're talking about dose. So we're going to have to extrapolate some way from this exposure out in the air into what happens inside of our bodies. And we're going to call that dose. And the equivalent dose, in particular, one of the things we're going to be unpacking today is the absorbed dose in biologic tissue as it relates to the type of radiation. Right? I'll say that one more time. It's the absorbed dose in my body as it relates to what exposed me. Because an alpha particle is going to be different from a beta particle, it's going to be different from an electron, it's going to be different from an X-ray. They are all going to interact with biological material differently. Okay? So when we're talking about these dose equivalents, right, effective dose and dose equivalent, we will be using either a rim or a sievert. And I've said that for my class, and also for the most part in our textbook, they're going to favor sieverts. Okay? Just because the amounts that we're dealing with are pretty small. If we are talking about an acute radiation syndrome, something that was caused quite a bit of damage, we might switch over to rim, right? Just because it's a little bit, it can handle those bigger numbers, right? But in terms of like converting from one to the other, I always just remember centigrade, right? Because centigrade equals 1 rad, right? So it helps me remember that conversion principle, okay? If we're talking about the absorbed dose, like just the amount that a person was exposed to, right, we're going to express that in gray. And we can have gray in tissue and gray in air. So sometimes we'll write that like gray sub T versus gray in air. Gray in air is a unit of exposure. This is probably one of the most confusing things that we'll talk about today. All right, so take some good notes right here. Gray in air equals exposure. It's just talking about the amount of energy floating around in the air. Sorry for my bad handwriting. Gray in tissue is actually telling us a dose. Sometimes if it's giving me a person's dose and the literature is very clear that what it's talking about is the patient received this dose, it might drop the sub T. It might just say, we do this a lot in radiation therapy, right? We'll say like 2 gray given today. We don't need to write the sub T. You can see I even struggle with writing the little tiny thing. But it's gray with a little tiny t below it, right? It means gray in tissue, the amount of energy in tissue. One reason why this is important is that when it comes right down to it, I don't expect anyone in this room to have a doctorate in whatever you're supposed to have a doctorate in to be able to calculate radiation dose. Because no joking, it's probably up there next to wizard degree. Like, has anyone seen any like programs advertising legitimately how to do magic or how to do like any kind of? No, I didn't think so. Try to find a program that teaches you radiation biology. Try to get a PhD in radiation biology. I have no clue how these people arrive at the weird government test sites that they arrive at, right? Where you have to be scanned into some weird door and it looks at your eyes or something to let you through it. I probably shouldn't even be putting this on YouTube because it's a super secret process for however you get to the point where you can actually calculate dose in someone's body. It's weird stuff, right? And in general, we'll call it dosimetry or dosimetrist, and I'll just say that's for the dosimetrist, right? So what I'm interested in for us today in this class is understanding just the basics of how they weigh this stuff out, right? Yeah, just the basics of what these terms mean and how they're applied. So, switching gears just a little bit. We just talked quite a bit about Electromagnetic radiation. That's one type of radiation. The other type is going to be particulate radiation, right? And I've already alluded to it some. These are forms of radiation that include alpha particles, beta particles, neutrons, protons, electrons, anything that's a subatomic particle, right? That could potentially interact and give enough energy to an atom to ionize it. We're going to call that particulate radiation, right? So these subatomic particles are ejected from atoms for various reasons, and they cause ionization by direct atomic collision. They're actually bombarding the atom and causing ionization. They might even cause something more than ionization to occur, right? So interestingly enough, no ionization occurs with a particle that's at rest. But of course, that's highly theoretical because the idea of a subatomic particle being at rest is something, again, for the dosimetrist. But this illustration here is just trying to show us that these different radiation sources, or I should say, these different radiation types coming from their various radiation sources have different thicknesses in which they'll displace their energy. Right? So an alpha particle, even though it has a lot of energy, it has so much energy it's going to get off real quickly, we could shield it with a sheet of paper. We can be shielded from an alpha particle with just a sheet of paper. Versus a beta particle, it would probably be stopped by a layer of clothing. Right? So probably the number one rule of dealing with particulate radiation, the nuke med people will tell you this, is just don't get it inside your body. Don't eat that radioactive hot dog. Right? Because if you can keep it outside of your body, your body's actually going to, your body and your clothing have sufficient shielding to protect you from particulate radiation for the most part. Right? Am I about right on that, or am I crazy?
We did do a study where they actually eat radiation.
Yes.
I know what you mean.
But the radiation that they eat, is it giving off gamma rays or? Yeah. So
That's how we detect it.
we don't want them to eat radiation, for example, that gives off alpha particles or beta particles.
Well, our PET studies are done with F-18, which gives off your gammas, but it also gives off the beta.
That's right.
That's why we don't stay in the room with them, and
Yeah.
they're in an enclosed space, because we can actually get that, and we don't want that because it interacts.
That's a really good
More
point.
likely to interact with the gamma.
Yeah, and when we looked at that ACR chart earlier, like in the trimester, we saw the PET CT was way up here next to the others in terms of dose, because they're calculating both for the gamma rays, the X-rays from the CT scanner, plus these beta particles now. And we're going to talk about why those beta particles are such a big deal. And what's motivating that choice. Versus these gamma rays they could sail through a cement wall and keep going. They are very, very high energy. In fact, they can exist in ranges that would cause interactions with the nucleus of an atom, right? They can be responsible for things like pair production, right? Let's talk a little bit about alpha particles. Our textbook mentions that they contain 2 protons and 2 neutrons. So we said they're just basically the nucleus of a helium atom. So that means it's a helium atom minus its electron cloud. But it has a whole lot of energy. And I think about it being like a bowling ball, right? This is the bowling ball on the pool table, right? If my electron is a pool ball, when I throw that bowling ball on the pool table, everyone's going to kick me out of the bar, right? Like you don't play pool with a bowling ball. But that's basically what alpha particles do. They have their purposes in God's grand scheme of things, but no one here on Earth knows what it is because we don't want to come anywhere near them, right? Even for medical applications, very rare that we'd be using anything like an alpha particle emitter, okay? So as an internal source of radiation, they can be very, very damaging, right? As an internal source of radiation, they can be very, very damaging. Especially if they're emitted from an isotope that's been deposited somewhere in the body, and it has to go through that decay process that the isotopes go through. It's going to continue. Each part of that decay process, it's going to emit another alpha particle. Versus beta particles, in beta decay, it may, like Stephanie said, emit both a beta particle and a gamma ray. So beta decay is a little bit different. And each element is very interesting, and again, something for the dosimetrist. We'll look a little bit at internal dose and talk about different common, different forms of particulate radiation related to some of the radioisotopes that we use in nuclear medicine and therapy. But a beta particle is much smaller. It is actually an electron that's been emitted from the nucleus of an atom, right? And what they say theoretically is that it's a neutron, right, that gives off a negative charge. So it expels an electron, which is weird when you think about it. But if I have a neutron is what? Is it positive, negative, neutral? Neutral, right? So if it expels an electron, what does that neutron then become? It becomes a proton, right? It becomes positive. So in the process of trying to find nuclear stability, this thing is going to eject an electron in order to form a positron, right? And it is now literally, as soon as it did that, it became a different element. If you think about that late at night, it'll keep you up because it's kind of weird, right? But it literally just became a different element on the periodic table. It just moved over a space, right? That's weird if you ask me. So nevertheless, these attributes of it mean that it's going to interact strongly with its surroundings, but not as strongly as the alpha particles. So we're kind of going down the spectrum in strength now. Ionize. High-speed electrons that are not beta radiation, this is the example that I used earlier from radiation therapy. We have certain mechanical devices like I can't remember, a linear accelerator, right, that can accelerate electrons very, very quickly, right? It uses microwaves and all sorts of crazy stuff to accelerate a stream of electrons at a target. If we move that target out of the way, we just have the high-speed electrons. So these high-speed electrons, their source is different. I can't stress this enough. They are not beta particles because they're not being produced by the nucleus of an atom. They're being produced by an electron gun and accelerated to high speeds. So their source is different. But we use these to treat superficial lesions in radiation therapy, and they would have to be artificially produced. We would have to use a machine to make these things, but high-speed electrons. And so, again, these have a little bit more penetrability than the beta particles. Protons. This is, like we said earlier, the positively charged component of an atom. There are some forms of nuclear decay that could actually eject a proton. For the most part, we don't really need to think about that in this class. We just need to know that they are protons. The number of protons in an atom tell us what element it is. And then neutrons are the neutral components of an atom. I kind of think of them as the glue that keeps the thing together. There should be the same number of protons as neutrons in an atom. And if there isn't the same number as protons in a neutron in an atom, that's kind of one of the defining characteristics of a radioisotope. But we've talked about neutron contamination, which can occur in the radiation therapy treatment suite, where we've annihilated the atom, the atomic nucleus of an atom, with a high-speed X-ray, right? Destroyed the nucleus of an atom, and now it's ejected neutrons all over the place. They are super high powerful things, and you definitely would not want to run into the radiation therapy treatment suite because the risk could be that you would inhale it into your body and it could cause significant internal damage. So, okay, well, let's talk just a little bit about why we've made this hard distinction between particulate and electromagnetic radiation, right? If they're all ionizing, what's the big deal, and what exactly differentiates them besides, like I said, one of them's like a bowling ball and one of them's like a pool ball, right? What we're talking about, we kind of put under the umbrella term of linear energy transfer, or LET, right? When we're talking about the LET, we're talking about a way to quantify the way that these different types of radiation interact. And so low LET radiations include X-rays and low-energy gamma rays, right? They have a low linear energy transfer. Moderate LET would be things like neutrons. They can penetrate a certain amount of tissue, but then they stop. And then the high LET is things like alpha particles, okay? That's the highest LET type radiation that we would be talking about. So this, you may recall, I tied earlier to indirect versus direct interactions with matter, right? So if it's a direct action, we're probably talking about a high LET radiation, right? So particulate radiation is responsible primarily for direct impact on DNA, right? That target molecule. An indirect action, we're talking about things that cause radiolysis of water, the production of free radicals. That's low LET energy, And so we're talking about X-rays, the lower energy gamma rays, and it can cause an indirect influence on DNA. So here again is just this illustration from our discussion last week of direct and indirect interactions. With direct, we have something directly causing a break in the DNA, right? A direct interaction with the DNA, versus an indirect interaction is one in which radiolysis of water occurs. We have the production of free radicals and possibly hydrogen peroxide, which then breaks the DNA. From the standpoint of the DNA or of the cell, it doesn't care whether it was an indirect or direct interaction, right? It doesn't care. It's going to go through this. It's going to initiate the same repair processes. The significance, though, is that when we're talking about direct interactions, we're probably talking about a pretty concentrated effect. So y'all may remember the image of the astronaut's blood sample, that where we had seen chromosomes that had just been completely atomized. Those were evidence of direct interactions, where there was some high LET, high LET radiation that was causing just total destruction of the DNA. So here again is that little petri dish showing ionizations, and it's comparing and contrasting low LET at the top, low LET energy, where we see it kind of moving and then bouncing and then moving and then bouncing, versus the ionization related to high LET energy. We see it giving off all of these interactions here and just blowing things apart, right? Now, one thing I want to point out on this slide, because there's a reason we've come back to this, is this keeps going, right? It keeps going. So each ionizing event has changed its direction and probably changed its energy some, but it keeps on going. So this is the one reason why I want to focus on this, is because this is where it gets flipped around in people's brains a little bit, is the high LET radiation, like the alpha particles and beta particles, they get stopped by a piece of paper. They give off all their energy really quickly and then they stop, right? The low LET energy, like X-rays and lower energy gamma rays, they will ionize and then go, and then ionize and then go, and then ionize and then go. So they will go straight through things, right? So, the reason I've had y'all dance is because now we get to talk about math, and I know how much people love math. But let's talk a little bit about how we're going to quantify these doses, right? So we've talked about the difference between particulate versus electromagnetic, and now we're going to talk about why that's significant when we're talking about dose, okay? So radiation quantity used for radiation protection purposes is when we talk about how it relates to the various types of ionizing radiation, whether it's particulate or electromagnetic, we are talking about an equivalent dose. We're saying you received this exposure, but it was from an alpha particle. You received this exposure to an X-ray. They are going to be different in the terms of the way that they interact with tissue because of their LET, right? So regardless, the unit of measure for this is going to be the sievert. Okay, so we'll receive some dose amount, right, in gray in tissue, and then we're going to multiply it by the type of radiation, like a factor based on the type of radiation. So this is going to allow us to calculate an effective dose, and so it is both occupational and non-occupational dose limits are based on these effective doses stated in sieverts. So here's why, this is the way that the scientists have quantified those different LETs and the way that they have a weight when we're calculating dose, okay? So when we were doing the low LET dance, right, energize, that weight is only about 1, right? So whatever my gray exposure to, like gray in air, if it's to X-rays, same thing in tissue, right? The weighting factor is 1. But if we're talking about an exposure to alpha particles, we might have a weighting factor of 20, right? Because it is a high LET particulate radiation. Crazy dance. All right. So then when we can combine that with the relative biologic effectiveness, what this is trying to do is give us an understanding of why we've got these different LETs as it relates to the biology of it, right? So we've talked about it primarily as it relates to the physics of it. This is trying to talk about it as it relates to the biology. And so they'll have some test dose amount. It's typically 250 like an exposure to 250 keV of X-ray, right? And then they're going to divide that by the dose response of whatever other kind of radiation a person could be exposed to. Okay? And that's going to give it relative biologic effectiveness. Right? If it's about the same, if 250 of X-rays is equal to the same as like 250 of this other radiation, they're equal, they're one, right? But if the LET of the other radiation is higher, right? If a smaller dose creates the same effect, then that's when we're going to start to see a dose factor that increases, like an alpha particle is 20, right? Because it takes a lot less exposure to alpha particles to create the same biological response, okay? Because we talked about how energizing it is. So as LET increases, relative biologic effectiveness increases. Just file that away in the back of your cabinet, because at some point you're going to see this goofy acronym, because it is on most of our boards, to recognize that RBE just means relative biologic effectiveness. When someone's talking about RBE in terms of our scope of practice, they're talking about high LET versus low LET. If I see something as a high RBE, then I know that it is a high LET energy radiation. And there's some more information on Washington Lever, page 60. By the way, Washington Lever is the radiation therapist textbook. It's a really good textbook. So in terms of breaking down LET or LET, RBE, and the dose, right, we have an absorbed dose that's going to be, like I said, given to us in gray in tissue, right? And this is the energy deposited in a kilogram of the substance by the radiation, right? To get the equivalent dose, we're going to have to multiply that dose in gray by a weighting factor. And when we do that, the unit's going to change to sievert, right? And then to get the effective dose, this is, again, more in the realm of the dosimetrist, but we need to at least have a ballpark idea of how they do this. We're going to need to multiply the dose times the weighting factor for the radiation times the weighting factor for the tissue, because different tissues in our body respond to radiation differently. And we'll talk about why that is as we get deeper into this material, but just know that that unit is also going to be sievert. So if we are talking about traditional units, up here we're talking about rads, and then rem, and then rem. That's in traditional. Okay? So again, this is something that I've found in the past students really grapple with this. So we're just gonna spend quite a bit of time unpacking what this equivalent dose means. Okay? Equivalent dose, right? EQD, I don't know how I just said, but EQD stands for equivalent dose. And this comes from a British website, so they've spelled ionizing differently from us. But we have an absorbed dose, and again, that's expressed in gray, right? We multiply it by a weighting factor here for the radiation, oh my goodness, and we get the same thing in sievert. We've just taken into account the type of radiation. Was it particular or was it electromagnetic, right? Now, if we really want to know what the effective dose is, how this dose was distributed through the person's body, we've got to find tissue weighting factors for every single organ that could have been receiving that dose, right? And this is why the dosimetrists get paid the big bucks, is because they sit there and they figure out weighting factors for like the liver versus bone marrow versus bladder versus kidneys, all of that stuff. We weigh out that dose in each of those different tissues, and we, again, express that in sievert. But this is why, for example, if you're talking to a physicist and you're talking about a dose that a patient received, they may look at you kind of funny. Because for them, there's no way to talk about patient dose, right? There's like the dose to the kidneys or the dose to the liver, right? They have to break it down. They're being very particular in the way that they use dose because they're talking about the effective dose. If we want to calculate the equivalent dose, don't be scared by this formula, right? All it's saying is the EQD, oh my goodness, I can't talk or right now. I think my sugar's dropping. It's going to be that dose in gray, right? That dose in gray times a weighting factor, a tissue weighting factor. That's all it's saying. Don't be scared by that goofy looking formula. It's just saying the sum of whatever, that E means sum, like from Excel spreadsheets, the sum of whatever radiation they were exposed to times the weighting factor for whatever those different radiation types were. So let's say an astronaut was exposed to so many gamma rays and also so many alpha particles. They can sum that radiation, but then also talk about the weighting factors for those different radiation exposures, those different types. And that's going to give us the equivalent dose. It's going to equalize all those different types of radiation. Now let's talk just a little bit about this, and I'm jumping ahead some in our textbook, but let's talk about tissue weighting factor, okay? Because our textbook introduced us to these terms, but then it just kind of leaves us hanging about what the heck it's talking about. All I want to say about tissue weighting factor right now is these have been established by extensive scientific reports, a lot of them from the ICRP, and they've looked at the way that radiation has affected these different kinds of tissue in given populations. Largely, again, the people who were exposed to radiation from Hiroshima and Nagasaki, nuclear weapons, right? And you can see they've kind of evolved and changed a little bit over time. So again, if I want to now calculate the effective dose, the first thing I need is that absorbed dose, that gray in tissue. How much were they exposed to? How much did their tissue receive? And then I'm going to multiply that by the radiation weighting factor to get an equivalent dose. So the first step to getting an effective dose is to figure out what was the equivalent dose. If they were only exposed to X-rays, then they're equal. But if they were exposed to X-rays and some particulate radiation, then that's where things get a little confusing. And we may have to use a radiation weighting factor. Once I have that equivalent dose, to finally get that effective dose, the EFD, I need to know the tissue weighting factors for every single thing that dose came into contact with. Do you ever need to do this in your work as an X-ray tech, or a radiation therapist, or as a nuclear medicine tech? No. This is outside of your roles and responsibilities, and you can be grateful for that, right? This does not sound like fun to me. This sounds like a really good way to be bored to tears. But it is significant in that when we're thinking about dose, we need to understand, we need to have a robust appreciation of the science that gives us this information. And we also need to have some respect for those people who work in our organization who look like, Egon Spence or something from the Ghostbusters. And this is all they do, right? Is just think about the way that, what were they exposed to, what was it, and then where did it land? So where this is significant for us, right, as X-ray techs, as nuke med techs, as radiation therapists, is any time there's a misadministration, number one, we need to report it, right? It's very, very important that we report any kind of misadministration of radiation. We need to be able to say what the misadministration was. I did a routine chest X-ray on Mr. Jones, right? But it turns out that was really Mrs. Jones, right? I wasn't wearing my glasses that day. I did a routine chest X-ray. I can tell that to the physicist. That means something to them. Okay, chest X-ray. That means I have a weighting factor of 1. I didn't ask them to drink any alpha particle emitting substances, right? Okay, chest, right? That's significant because the chest has it has lungs, it has liver, maybe a portion of the liver, it has ribs, it has all these things that different doses are going to influence differently, right? So when we report anything to the physicist or to the RSO, this is why I'm dragging this point out, is because it's important that we say when it happened, what it was, right, and where it was, right, where on the patient's body it hit them, right? When it happened, what it was, and where it was on the patient's body. Because they've got to do all this for us. And the more information I can give them about that, the more accurately they can calculate an effective dose. Here again is the formula for calculating effective dose. I may ask you to do this at some point, right? You would be given an amount of radiation, like say 100 keV of X-ray. You would need to know the weighting factor. I would give you a table saying the weighting factors of different kinds of X-rays or different kinds of radiation. You would pull the weighting factor down, right, and drop it into your formula. And then I would say it was the exposed area was the lung, the heart, the ribs, etc. You would pull that into your formula as well, and you could say the dose to the heart was X, the dose to the lungs was X, the dose to the liver was X, right? But just know, if you get a formula, if you get a problem and it's got a bunch of tables on it, if it has 2 tables on it, I'm probably asking you for effective dose. If it has 1 table on it, I'm asking you for equivalent dose, right? Does that make sense? Because again, I'm not expecting us to be physicists, but we need a robust understanding of this. So when the physicists calculate their dose, these are the areas that we generally disseminate to the public. So earlier when we were talking about 3 Mile Island and the kind of exposures that people receive from 3 Mile Island, a lot of what they were looking at was this, and asking, okay, what kinds of doses happen to the general public as a result of it? And their response might be that the entrance skin exposure was essentially nothing, right? Because what we're dealing with is a particulate radiation, and we're interested in whether or not they actually drank the water that had stuff in it. But then the bone marrow dose might have an influence, especially if we're talking about something like iodine or radium, which has an affinity to bone, right? And then gonadal dose, right? This is one of the primary ones that we will use in X-ray, right? Because we are interested in, was the patient shielded? What kind of internal scatter might have occurred? And they can calculate for that and come up with an estimated gonadal dose. And then the main reason for that, driving that, is of course pregnant women, because anytime we have an inadvertent exposure to radiation, we're going to need to ask questions about, okay, well, does this pose any risk for childhood cancer? Does this pose a risk for mental retardation? Does this pose a risk for any kind of complications related to that person's pregnancy? Okay? All right.